In the absence of deadlock prevention or deadlock avoidance algorithm, a deadlock may occur. You can recall from the last lecture that deadlock prevention or deadlock avoidance algorithm, they ensure that a system will never enter a deadlock state. However, in the absence of these algorithms, a system may enter a deadlock state. In this case, system must provide a detection algorithm as well as a recovery mechanism. Detection algorithm will be required to determine the presence of deadlocks in the system, whereas recovery scheme is needed to recover from a deadlock state. Detection and recovery mechanisms incur some overhead. The cost of maintaining the necessary information and executing the detection algorithm. The price that we have to pay is to maintain the necessary information. This information will be required by the detection algorithm to determine the presence of deadlocks in the system. So we have to incur the cost of maintaining this information as well as executing the detection algorithm that will make use of this information to determine the presence of deadlocks in the system. Secondly, there are potential losses inherent in recovering from a deadlock. In order to recover from a deadlock situation, we might have to terminate some of the deadlocked processes, or we might have to preempt resources from the deadlocked processes. In both these cases, we might lose some of the partial execution results of the processes. Wait for graph. If all resources have only a single instance, then we can define a deadlock detection algorithm that uses a variant of the resource allocation graph called a wait for graph. So wait for graph is nothing but a detection algorithm. Wait for graph will be used to detect the presence of deadlocks in the system. However, this algorithm will be used only when the resources have only a single instance. Wait for graph consists of nodes and edges. Nodes represents the processes in the wait for graph, and an edge from process Pi to process Pj. This edge means process Pi is waiting for resources which are held by process Pj. This figure shows a resource allocation graph and the corresponding wait for graph. We can see from this figure that resource allocation graph consists of two types of nodes, the process nodes and resource nodes. An edge from a process to a resource node, it represents that process is waiting for that particular resource type. Whereas an edge which goes from resource to some process node, that edge indicates that resource has been allocated to that particular process. Now we can collapse these two edges into one edge in the corresponding wait for graph. An edge in wait for graph from one process to the other process indicates that process is waiting for that resource which is held by the other process. Towards that edge is leading us. An edge Pi to Pj exists in a wait for graph if and only if the corresponding resource allocation graph contains two edges. The first edge is Pi to Rq and the second edge is Rq to Pj. So these two edges can be collapsed into a single edge, that is from process Pi to process Pj in the wait for graph. As before, a deadlock exists in the system if and only if the wait for graph contains the cycle. We have already discussed that the presence of a cycle in resource allocation graph means system might lead to a deadlock situation. Likewise, in wait for graph, presence of a cycle means that system is in deadlock state. For this particular case, we can see from the wait for graph that this system is in deadlock state because there exists a circular wait condition, and this circular wait condition involves the processes like process P1, which is waiting for the resources held by process P2, which is further waiting for the resources held by process P3, and P3 is waiting for the resources held by process P4, and P4 is waiting for the resources held by process P1. So there is a circular wait condition that exists in this cycle, or in other words, a cycle is present in this wait for graph. So this means there is a deadlock situation. Wait for graph is maintained by the system to detect the presence of deadlocks. System will periodically invoke an algorithm that searches for a cycle in the graph. If there is a cycle, this means there is a deadlock. An algorithm to detect a cycle in a graph requires an order of n square operations, where n is the number of vertices in the graph. When we have several instances of a resource type, in that case, wait for graph is not applicable. In this case, we use a detection algorithm with several data structures. The first data structure is available. Available is a vector of length m. This vector indicates the number of available resources of each type. Allocation. Allocation is a matrix of order n into m. This matrix defines the number of resources of each type currently allocated to each process. Request. Request is another matrix that indicates the current request of each process. If request ij is equal to k, then process pi is requesting k more instances of resource type rj. Detection algorithm. Let work and finish be the vectors of length m and n respectively. Work is assigned available, and in second step, in part B of the first step, there is a for loop for I is equal to 1 up to n. If allocation I is not equal to 0, then finish I is false. Otherwise, finish I is true. In the second step, we find an index I such that both condition A and condition B holds. Condition A is finish I is equal to false, and condition B is request I is less than or equal to work. If no such I exists, then go to step 4. In step 3, work becomes work plus allocation I, and finish I becomes true. Then we again go back to step 2, where we find another I for which finish I is false as well as request is less than or equal to work. In step 4, if finish I is equal to false for some I where I is in the range 1 up to n, then the system is in deadlock state. This means if finish I is equal to false, then process Pi is deadlocked because this process has not completed its execution yet. The detection algorithm investigates every possible allocation sequence for the processes that remain to be completed. Let's take an example to explain the detection algorithm. Suppose there are 5 processes in the system, process P0 up to process P4, and there are 3 resource types, resource type A, type B and type C. There are 7 instances of type A, 2 instances of type B and 6 instances of type C. At time t0, process P0 has been allocated 1 instance of type B, and this process doesn't need any further resources to finish its execution. At time t0, process P1 has been allocated 2 instances of type A, and this process can further request 2 instances of both A and C. Process P2, it has been allocated 3 instances of both type A and type C, and it doesn't request any further for resource types. Process P3, it has been allocated 2 instances of type A, 1 instance of type B and 1 instance of type C. It can further request 1 instance of type A. Process P4, it has been allocated 2 instances of type C, and this process can further request 2 more instances of type C. Currently, there are no available resources in the system because all the resources they have already been allocated to the processes, as you can see from the allocation matrix. Now we can see that process P0, it doesn't require any further resources to finish its execution because its request matrix, it contains value 0, 0, 0. So process P0 will finish its execution and it will release its allocated resources, and it has only 1 instance of type B, so it will return 0 instance of type A, 1 instance of type B and 0 instance of type C. So adding the existing available resources and the released resources by process P0, we will get 0, 1, 0. So these are the new available resources in the system. After this, we can see that process P2 can finish its execution without requesting any more resources. And once process P2 it completes its execution, it will release these instances, that is 3 instances of both type A and type C. So we can add these instances of the resources to the existing available resources, that is 3, 0 and 3. So we will get 3, 1 and 3. So this is the current value for the available matrix. Now process P3, it can complete its execution, and this process need only one instance of type A, and this request can be easily granted from the available resources because we have 313 in the available matrix. So we can allocate one instance from the type A. So this process will also complete its execution, and once process P3 has completed its execution, it will release these resources which have been allocated to it. Remember, it has requested for one more resource of type A, so there are now 3 instances of type A which are allocated to process P3, and likewise we will subtract one from here because now there are 2 instances of type A, 1 of type B, and 3 of type C in available matrix. So when this process P3 will finish, it will return 3 instances of type A, 1 of type B, and 1 of type C. So we can add those values to the current available matrix. So we will add to this matrix 3, 1, and 1. And the new values for the available would be 5, 2, and 4. After this process, P4 can finish its execution. This process needs only 2 instances of type C to complete its execution, and because we have 4 instances of type C, so we can easily fulfill this request of process P4. We will allocate 2 resources from these 4 instances of type C to this process P4 so it could complete its execution, and after this process has finished its execution, it will also return its allocated resources which we can add to the available matrix. So we can find that this sequence, that is first process P0 has completed its execution, then process P2, afterwards process P3 will complete its execution, then process P1, and finally process P4 will complete its execution. And this sequence will result in finish I is true for all I. This means system is in safe state and there is no deadlock. All the requests can be easily granted. Let's consider a case when process P2 requests an additional instance of type C. So this is the previous snapshot of the system at time t0, and what is the new scenario? Scenario is process P2 is requesting one additional instance of type C. So this means the request matrix would be 0, 0, 1 for process P2. Why we have changed this 0 to 1? Because P2 is requesting one more resource of type C. Now let's see what would be the state of the system. Either we can fulfill this request or not. Now suppose process P0, it can safely complete its execution because it doesn't need any further resources. So once process P0 has completed its execution, it will return one instance of type B. So the available matrix would become 0, 1, and 0. Now let's try to find another process which can complete its execution. Let's try about P1. Okay, P1 needs 2 instances of both type A and type C to complete its execution. We cannot fulfill its request from the available resources because we don't have enough resources to grant the request of P1. Okay, what about P2? P2 needs one instance of type C, which we doesn't have in the system. So P2 cannot complete its execution. So both P1 and P2, they cannot complete their execution. Okay, let's consider the case for P3. P3 needs one instance of type A. Okay, we cannot grant its request because we don't have any instance of type A. So P3 will not be able to complete its execution as well. Okay, what about P4? This process needs two instances of type C. Again, we don't have enough resources available, so this process cannot complete its execution. So we can conclude that either we can claim resources held by process P0. P0 can complete its execution successfully and it will release the resources, but still we have insufficient resources to fulfill the requests of the other processes in the system. Hence, there is a deadlock in the system because these processes will enter into a wait state. All these processes, that is process P1, process P2, process P3 and process P4, these four processes will enter into a circular wait condition. That is, they are holding few of the resources and they are waiting for the resources which are held by the other processes in this circle. So there exists a deadlock in the system that consists of these four processes. Detection algorithm usage. When should we invoke the detection algorithm? The answer to this question depends on how often is the deadlock likely to occur. And it also depends on the other factor, that is how many processes will be affected by deadlock when it happens. Considering these two options or these two parameters, we can say that if deadlock occurs frequently, then the detection algorithm should be invoked frequently. Remember, a deadlock occurs whenever we cannot grant the request of a process for some resources. So every time when a process makes a request for the resources, we have to invoke the detection algorithm. However, invoking the detection algorithm for every resource request, it will incur considerable overhead in terms of computation time. This means whenever a process will request resources and this request cannot be granted, we have to execute a detection algorithm. And every time when we execute this algorithm, it will need computation time. Hence, computational time is wasted because this time is being used by the detection algorithm. This is not being used by the processes. Another answer might be that a less expensive alternative is simply to invoke the algorithm at regular intervals. This means after fixed regular intervals, maybe we can invoke the algorithm after every 30 minutes. And this is a less expensive solution as compared to the previous one where we have executed detection algorithm whenever a process will request the resources. Another case might be that we can invoke the detection algorithm when CPU utilization falls below a certain value. For example, if CPU utilization decreases to 40%, this means system is turning idle because some processes might have deadlocked. They are in waiting state. They are not using the CPU. So if CPU utilization drops to a certain value, we can decide to invoke a detection algorithm. Another situation is that algorithm is invoked arbitrarily. This means at arbitrary points in time we can invoke this algorithm. These are not regular intervals now. We will randomly choose that when to execute the algorithm. However, if we choose to invoke the algorithm at arbitrary points in time, then it can result in many cycles in the system. In this case, we generally cannot tell which of the many deadlocked processes caused the deadlock because there are more than one cycles in the system now. So it is difficult to tell that which processes have caused the deadlock. And obviously the recovery will be more difficult in this situation.